Hello, everyone. Gold is an important metal. Throughout history, we have adored it as jewelry and valued it as currency. Nowadays, we're increasingly relying on it in some medicines, and notably in circuitry in the context of modern electronics. And you can eat gold. Gold even has an E number. But where does gold come from? Gold is found naturally in rocks and ores, but only in a few places around the world. Around 3,000 tons of gold was mined in 2017, with China, the US, and Australia being the major contributors. Even then, gold is found alongside other metals and in really low concentrations. You can only get up to a gram of gold out for every ton of rock mined. This is a problem. We go to extraordinary lengths to get the gold we treasure. 90% of the world's gold comes from mining processes that treat the crushed rock and ore with large quantities of notoriously toxic cyanide. Though this may allow for the efficient separation of gold from the rock, through accidental leakages and blatant dumping of hazardous material, cyanide reaches local water supplies. This has a devastating effect on the local environment for both wildlife and workers. In fact, the use of cyanide makes gold the most toxic metal to produce. We also use incredible amounts of energy and resources mining and processing tons of rock to get just a few grams of gold out. To get gold from crushed rock into gold ring requires many energy-intense processing steps, including, but not limited to, physical mining, crushing, storing, transporting, separating, refining, and many, many more. Metal production in general demands 10% of the world's energy supply and also produces significant quantities of carbon dioxide and other harmful emissions. For every kilogram of gold produced, 12,500 kilograms of carbon dioxide is released. This is the second highest global warming potential of all elements in the periodic table. These mines also create a lot of waste, and I'd like to give you a sense of scale of this. This is the Superpet gold mine, formerly Australia's largest open-cast gold mine, producing 28 tons of gold every year. This single mine is 1.5 kilometers wide, 3.5 kilometers long, and 2.5 kilometers deep. This can be hard to visualize for a single mine, so I'd like to give you some perspective. You might be able to make out a little speck on one of the roads in that pit. That's actually a dumper truck like this one that transports crushed rock from one site to the next. How big is that dumper truck? Well, here's a worker standing next to one. These mines are vast. Think of how much gold we get out of these mines compared to rock, how much rock we've had to displace, the vast majority of which we've simply disposed of. In fact, it can take 20 tons of rock to make that one gold ring. This is the severe and detrimental impact we have on the environment. Given our reliance on gold, it is important for us to look to other sources of the metal and for more efficient metal recovery processes. So, we need a better solution. From 1 ton of rocks, you can get up to a gram of gold, but you can get 300 grams of gold from 1 ton of mobile phones. As there's much more gold in circuitry than rocks, it's much more efficient and environmentally friendlier to recycle gold from waste, electrical, and electronic equipment called WE instead of mining it. Think of how many phones you've had in your lifetime. Now think of what's happened to those phones when you got a new one. Maybe you gave it to someone else to use. Maybe it's in the bin. Maybe it's in that drawer at home. But how many were recycled? People today will now have, on average, 40 phones in their lifetime. Yet in the EU, less than 20% of WE is recycled. The vast majority of waste electronics are sent straight to landfill. So you might be thinking, well, how much gold's actually in my phone? What's the point in recycling it? The phones we value so dearly have around 30 milligrams of gold in them, or around 85 pence worth. This might not seem like a lot, so if I was to gather everyone's phone in from this conference of around 700 people, then we'd have 21 grams of gold, or £630 worth, enough to buy 2/3 of a new iPhone XS. This might not seem like the best deal, so how about this? Globally, 40 million tons of WEEE is generated every year. This is an urban gold mine. In gold alone, this is worth £9 billion. If we include all metals and waste electronics, this goes up to £22 billion. And this is only set to rise as the sales of electronic products, and therefore amount of electronic waste, is increasing every year. At the start, I said metals are found in low concentrations alongside other metals. Yes, there's gold in your phone, but WEEE has many metals in it. There's silicon and potassium in the glass. The touchscreens are made of indium and tin. The batteries are full of nickel, lithium, cobalt, all in an aluminium casing. Our LEDs require lanthanides to give us brighter colors and better contrasts. The circuit board itself has gold, mainly copper, tin soldering. All these metals, 60 different possible elements in your smartphone, and gold is definitely not the most abundant one in there. So how do I get gold out of your phone? This is where my research comes in. I am a chemist, and I investigate chemical methods for the recovery of metals without having to use toxic reagents. We said metals are found in low concentrations alongside other metals, so we need some way to separate and concentrate them. One common way of doing this on an industrial scale is to use a technique called Pyro Metallurgy, essentially melting out the metals from the source. But this requires high temperatures, lots of energy, and can be really highly polluting. One particularly efficient way and greener way of separating metals on an industrial scale is to use a technique called solvent extraction, which has two liquids. First, we dissolve all of the metals out of your phone and into an acidic water solution. This gives us a mixture of metals, including copper, iron, platinum, palladium, and gold, which is the most valuable to recycle. The other liquid is an oil, which sits on top of the water but doesn't mix into it, much like olive oil sits on balsamic vinegar. We design molecules called extractants that transport the metal of choice out of the water and into the oil. If we can do this selectively, then we can separate gold from the mixture. This is a sort of molecular level gold panning. We're sifting through all the metals in the mixture and only collecting the one that we want. So how do we get selective gold separation? Every metal in the water has a certain size, likes to form certain shapes, has a certain charge, basically has a preferred chemistry. For example, gold likes to form flat squares. Platinum likes to form octahedra. We design molecules that can discriminate between the metals based on these features, bind to gold and only gold, and transport it into the oil. This selectivity is a bit like the child's toy, where you can't get the round peg in the square hole. Our molecules are particularly efficient. Not only do they recognize gold squares, they transport multiple at once as molecular golden nuggets. This gives us more metal out for less chemical used. We can then separate off the gold-containing oil and treat it in a couple of steps to give us back the gold in an overall more efficient and less damaging process compared to traditional mining methods. Here's what it looks like on the small scale in the lab. Remember, we take your mobile phone, dissolve it in the acidic water solution to give what we like to call mobile phone solution. For interest, that green mixture on the right has a concentration of 10 phones per litre. You contact that mixture of metals with the colourless oil that contains the extractants. That's the solution on the left. Mix the two together, and as the two liquids separate out, we see gold move from the lower mixture up into the oil, achieving separation. We then physically separate the two liquids and treat the oil in a couple of steps to give us back the gold metal. This technique is already being done on an industrial scale. Here's an example for copper. First, you take your crude rock containing copper and other impurities and dissolve or leach the metals into the water solution. Here it's called the pregnant leach solution. That's that vast pond you see on the left. That's our aqueous mixture. Somehow then we separate and concentrate out copper from the mixture. Here we'll use solvent extraction. That's what you see in the middle. This is a massive mixer settler tank running in continuous flow with isolated and separated copper running out of the end of it. That's rivers of copper coming out. Lastly, we take that now isolated copper and reduce and refine it to give the metal back in its zero oxidation state, and there you see copper plates formed upon electroreduction. So how do we fit into this picture? As a reminder, we've dissolved your phone in an acidic water solution. Gold exists as the square gold complex, so that's our target molecule. There are already a number of available commercial reagents to separate gold, but they all suffer a few drawbacks. They must be used neat. You can't use them in the solvent of choice. They're volatile and hazardous, so that adds safety and cost concerns. It's difficult to strip them. It's difficult to get the gold back out from them. Sometimes you resort to them to burn off the chemical. Our new reagent is a remarkably simple primary amide that has marked advantages over what's currently available, and I'll now show you how, as well as how well it works. Remember those molecular golden nuggets I was talking about? Here they are. This might look confusing. This is just a computer simulation drawing from experimental evidence, showing the dynamic self-assembly of these extractants coming together. As they come together, they pull in these gold squares. It's this what gives us selectivity. Only gold of its certain size, shape, and charge can fit in these little pockets between the reagents. It's also this dynamic assembly that's giving us the ability to easily get the gold back out of it. By simply washing this with water, we can disassemble the whole thing, and gold falls out into its new isolated solution. So that's how this works. This is how well it works. Here's some numbers. These green bars represent the relative amounts of each of the metals found in our mobile phone solution. This is assuming complete dissolution of the printed circuit boards. We've got lots of copper, some aluminium, zinc, nickel, iron, tin, and so little gold, we've had to change the scale twice. So these green bars, the relative amounts of each of the metals found in the mobile phone solution. These red, blue, and grey bars represent the relative amounts of each of the metals loaded into neat solutions of the 3 currently available commercial reagents. We see all 3 of them are strong gold extractants. They can recover most of the gold from solution. But they're also taking on significant quantities of tin and iron, so they're not very selective. Our new reagent is shown here in these gold bars. So our new reagent is also a strong gold extractant, able to recover most of it from solution, but importantly, it's taking on nowhere near as much tin or iron. So our new chemistry is a lot more selective than what's currently available. Those were extractions using neat solutions of the 3 commercial reagents, but a dilute solution of our new reagent. If I drop the concentration of the 3 commercial reagents down to the same level as our new reagent, suddenly we see they stop working. So not only is our new reagent a lot more selective, it's also a lot more efficient, requiring less compound around to achieve more separation and more recovery of more gold. How does all of this fit into the bigger picture? Yes, we have new chemistry, but for what purpose? What we're trying to do is help create what's called a circular economy. That means, after going through all the effort of getting our metals in the first place, instead of throwing our products away at the end of their lives, we're aiming to recycle as much as possible to the benefit of the economy, the environment, and society. Oops. And whilst there are many advantages to recycling gold from weed, there are still so many challenges we need to address. There are 60 different elements in your smartphone. Gold's not the only one in there. Can we recycle every single metal we've bothered to get out of your mobile phone? Yes, we can. That's what we're doing as chemists. But ultimately, we have to. It's been predicted that if we continue at today's rates of consumption, production, and attempts at recycling, we only have 30 years left of copper, 13 years left of indium, and we might have already run out of some lanthanides. Other questions we need to address. Can we reduce the amount of metals we need in our products in the first place? Can we get the next advanced technology that means we don't need gold or indium or lanthanides? Can we reuse parts of mobile phones that are already existing? Can we design products such that working components can be removed without having to destroy the whole thing? Can we design for reuse? Recycling, yes, but we need to be careful about making the most efficient steps along the way. What can we do now to address these problems? We need to work together. We need to work with scientists and engineers to make sure we have access to bulk materials and can deal with them efficiently. We need to work with governments and businesses to make sure we have the infrastructure, incentives, and framework in place to make sure we can deal with enough waste, collect it efficiently, dismantle it efficiently, process it efficiently. Because ultimately, the value of what we recover has to be greater than the cost of recovering it. We need to work together to now actively choose to recycle to make sure we can still have access to metals that don't cost us the earth. At the start, I said, gold's an important metal. We adore it in jewelry, value it as currency, rely on it in modern electronics. But where does gold come from? Together, the answer is we, because we are golden. Thank you.